Okay, so today we have like a lot of really fun stuff to talk about, but like we've talked about somewhat about rent, we've talked somewhat about WASM, but we can talk more about merkle tree constructions, we can talk about like a lot of things about execution, some later protocol improvements, including like how things like Starks could get integrated and how data availability proofs could get integrated, various cryptographic upgrades, and a bunch more on Casper and sharding topics that we didn't have a chance to cover yesterday. So yeah, and let's like start talking about stuff.
I mean, one of the things I'm quite excited about is the third one, the new random number generator and the 5-second blocks. I mean, a lot of the hard work we're putting at the core of sharding can be reused by applications, which is very cool. Hopefully, we'll have a random number generator which is really, really strong, which means you can kind of use it as a default for the applications, even for high-value lotteries, hopefully, which would be amazing. And the 5-second blocks, that's not only, there will also be probably quite low variance. So hopefully we'll build a system whereby the shards can continue operating at every single heartbeat, even if the beacon chain bad things happen up there, in terms of, for example, the proposer of the beacon chain aborting and causing the whole system to stall for 5 seconds.
Yeah, so I guess one important thing to think about is like what is the minimum number of seconds that actually is safe. And so for like you can go a bit to kind of different extremes here, right? So like for example, Dfinity is managing its test that totally fine with like 900 millisecond block times, but the reason they're doing that is because all of their nodes are basically in the same cloud hosting provider, at least right now. So it's like my general this is a question mark, and like people have different views, but my own philosophy is that obviously it should be possible to run a node just on a laptop, like if that's just connected to the internet, and with a regular internet connection, and just doing things by yourself. And that basically whatever the incentive structure is, it should be that whatever you can earn doing it that way should be like fairly close to what you can earn with a kind of theoretically optimal setup, right? So kind of not like, that's not assuming that that we're going to assume that everyone actually will be doing it that way, but the point is to at least like make it possible and not add pressures that kind of drive people toward the same computing providers right from the start. So with that in mind, right, one of the minimums is obviously like the amount of time it takes to verify a block plus 2 times network latency. And that's like network latency in general, like, and if you look at the Ethereum blockchain now, blocks are taking something like 1 to 3 seconds to propagate, depending on circumstances. And the EVM obviously is running at full capacity and has its own various efficiency issues that this particular design is not going to have, because the state of the beacon chain is and we've already calculated this, is going to be less than 400 megabytes, meaning that you can just keep the whole thing in RAM, so you don't have like I/O issues, and a lot of and the beacon chain itself does not run an EVM, so there's a lot of edge cases that you kind of don't have to be worried about. But at the same time, you do want to have some room for slack. Now, one reason why proof of stake can be you can be more aggressive on your parameters with proof of stake than you can be with proof of work is because proof of work is a Poisson process. So what that means is that if you have a block time of 14 seconds, that basically means every millisecond you have a 1 over 14,000 chance that a block gets created. And so if network latency is, say, 2 seconds, then what that means is that whenever a block gets created, there's a 1 over 7 chance that some other block is going to be created around the same time. And that both reduces the performance of the network and makes it more vulnerable to 51% attacks that have less than 51%. And it creates a centralization vector where pools that have better connections can already be shown to have substantially lower uncle rates, right? Like basically Ethereum, the current proof of work chain, uncle rates do vary fairly significantly. And so if it weren't for the uncle inclusion mechanism, the whole thing probably would have centralized much more significantly by this point. So with proof of stake, on the other hand, you have these fixed slots, and you know that as long as a block can get propagated within the amount of time before the next slot appears, then you're relatively fine.
I mean, another thing that proof of stake allows you to do more easily is have a slashing condition if the proposer who's assigned to the slot makes two different proposals, so basically equivocate at a given height. So that should mean that you should get confirmation faster. I mean, that's also in addition to this spectrum of confirmation that I was talking about, where you'll start getting attestations and all these other signatures much, much faster, well within the 5-second block time. So that's nice.
Yeah, so in terms of what actually needs to happen, right? Within each block height, basically you have a block that gets published, then you have all these attesters that need to submit their attestations. The attestations make their way through the network, they get aggregated, and the next block producer basically aggregates the attestations, makes an aggregate signature, and publishes their block. So in the best case, it requires 2 rounds of network interaction between the participants.
So I have a question about this synchrony assumption. There was a paper at some point by Raphael Pass and a few others who looked at sort of the Bitcoin model and concluded that basically in order to reach eventual consistency every time your block interval had to be several times your network delay. So I wonder in related questions, what would happen if you had, let's say, a temporary partition that was maybe a few times longer than the slot interval, and would the network naturally resume availability after stalling, or would there need to be a manual?
The network would probably not stall, it would just progress more slowly. And realistically, the Casper checkpointing would probably not stall, right? So I expect the micro performance to degrade, but the macro performance, basically, because you have this sort of structure layered on top where everyone's voting on a checkpoint every few minutes.
So you're saying the epoch length is long enough to be equivalent to a long block interval, and you don't care what happens inside the epoch?
Yeah. Basically, if the network latency is in between the block time and the Casper epoch time, then I expect that, obviously the blockchain will proceed forward more erratically, but it'll still make progress and it'll still do what people expect. The main cost is that under those conditions, there will be incentives to have much better connections than everyone else, and so if that becomes the persistent state of events, then that creates centralization risks.
I think you've written about this before, but just to remind me and other people here, what is the trade-off as you see it between a 5-second block and a 10-second block?
So the main trade-off is that 5-second blocks improve usability relative to 10-second blocks. So on average, you have to wait 2.5 seconds to get included instead of on average waiting 5 seconds. This also reduces the monopoly power held by individual miners, because basically an individual miner would only be able to delay any particular transaction by 5 seconds instead of 10. The risk is basically that the shorter the block time goes, then first of all, depending on the algorithm, if your algorithm is dependent on synchrony for safety, then obviously if block time becomes too fast, it becomes unsafe. But Casper is safe under asynchrony, so it's not going to revert finality, and even the attestation structure of the chain itself stabilizes it considerably in practice.
Yeah, for something like usability, it's not linear, right? So what are the inflection points in your mind?
Yeah, so I think there's definitely a few. So there is holy grail latency, which is basically you click and it happens before you even notice, so basically server level. That's not really achievable in a public blockchain except with channels. The second level is when you get to the like 1 to 2 second level, then it becomes like really comfortable to use point of sale systems. And if you get to the 5 to 10 second level, then like there definitely are, like if you look at existing credit card payments in a restaurant, like that's roughly their latency already. So it's like it is definitely at a point where you have kind of enough latency to be usable for a bunch of things, but you do kind of keep gaining with every second that you can knock down. If you get into longer periods of time, so basically anything longer than Ethereum, then like there comes an inflection point where you have to kind of go AFK after you send a transaction. And that, when you hit that inflection point, then like that's in some ways a qualitatively lower level of experience. So it definitely at least wants to be on the right side of that. Another thing that we, Carla, do you have a very valuable question?
I have a mildly valuable question. Probably not very valuable.
Okay.
So the guarantees that you get after 2.5 seconds, like how do we maximize those, or like what are the kind of scary things that could happen?
Sure. So here is the rough kind of timeline, right? Actually, I'll diagram it, right? So t equals 0 is like you send a transaction, right? Then t equals 1 is the time when you as a merchant receive a transaction and you have common knowledge that most of the rest of the network received that transaction before any double spend because you haven't seen the double spend. So if we have some application where, like in the case where miners are nice and refuse to include double spend, so basically the Bitcoin Cash model, you get kind of the Bitcoin Cash style security here. Now Ethereum at present does replace by fee, but like you could imagine hypothetical structures built as layer 2s on top of Ethereum that don't do replace by fee. Then over here, at some point along this area, and like we'll say on average, like at some point over here, so like basically t is somewhere between like 1 and 6. If the block time is 5 seconds, then this is the point where your transaction gets included into one block, right? When your transaction gets included into one block, then basically the default path is for the transaction to get accepted. The only things that could happen are, number one, the block producer themselves maybe had double spent, or number two, possibly the block producer themselves had like equivocated and made two different blocks. Or number two, there's some other block producer, so say the next block producer comes early or like otherwise creates a block, and for some reason that block gets accepted by the network. So both of these have like a fairly low probability, but it's still a significant one. So that's kind of level 2 of confirmation. Now level 3 is when you start getting attestations on top of this, right? So you start getting actually I could point out, by the way, that this is all happening not inside the beacon chain, this is happening inside of a shard. So level 3, in the shards, you can also have an attestation structure. And so over here, like basically, T is between, I don't know, something like, we'll say like 2 and 8 is when you start getting attestations on this block. Now, if you start getting attestations here, then it's harder for these competing blocks to win. And once these attestations exceed once these attestations exceed 50%, like basically for a competing block at the same height to reach the same attestation level, like somebody has to get slashed. So that's a higher level of security. Now, technically, of course, you could get like some block that gets created over here, and then this ends up getting attestations, but that's considerably harder. Then over here, your next point is something like T, I don't know, like possibly 6 to 11, and that's when you have 2 blocks, and then this continues. Then your next milestone is probably when you have a crosslink, And the first milestone is when the crosslink starts getting formed, right? So this could happen in, I don't know, like let's say on average, somewhere between 1 to 10 minutes. So let's say 60 to 600. Crosslink starts getting formed. Next milestone, the crosslink ends up getting included into the chain, and this could possibly happen over time. So let's say this could be, I don't know, like 65 to 700. Crosslink gets included into the chain. Then, wherever the crosslink is, that point gets justified. So basically, that block by itself ends up getting more and more confirmations. And then eventually, that block gets justified, and that might happen in, I don't know, like in general, like T maybe 70 to like 1500. And then it'll get finalized, and that might be T, I don't know, like 370 to 2000 or something like that. And then at this point, like basically, this block ends up justifying whatever this ends up finalizing whatever this is, and at this point you have kind of like some degree of finality. And then after here, like basically you get kind of more and more indirect confirmation that nothing invalid was finalized, and so the chain really is final.
Wow, cool.
I understand that the RNG is still not finished, but how can clients that are out of sync resynchronize with something completely random? Is there like the seed encoded in a block, or?
Yes, so it's not random, it's pseudo-random, right? So it is fully deterministic, and it is like you can calculate it is part of the state, and you can calculate everything you need to know by downloading and running the blockchain.
So in that timeline, when I buy a coffee at a shop, when should it consider?
For coffee level, probably somewhere around here is okay. Actually, you know what? No, for coffee level, this is okay, because if someone double spends you, then you know that they're being evil, and like basically, practically speaking, right? It's technologically harder for most people to double spend than it is to leave a restaurant and like leave a bunch of $5 bills on the table so that they can't figure out that you didn't pay enough until you're already ran off and you're half a kilometer away. So it's like the level of security you need for in-person payments, and actually even a lot of online transactions, is super low. Like because like if you think about categories of purchases, right? Number one, eBay. Well, if you double spent it, you cancel. Number two, ordering from a restaurant. Well, if you double spent, well then they can cancel. Number three, booking a flight, they can cancel. So for anything in person, well, if it happens very soon, then you're right in front of the guy. The guy knows you're a thief, and he can like call the police and whatever, right? So basically the level, like for most categories of payments, like basically the Bitcoin Cash people are like pretty much correct in that the level of safety that you need is very low because payments happen in like this context. If you're thinking of transactions going beyond payments, then things do get tricky. So like for example, things like lotteries, things like actions inside of smart contracts that take a longer, that are more complicated, especially kind of like commit reveal schemes. Like if you commit and then reveal and then part of the blockchain gets double spent, then you can kind of replay the game, but then knowing everyone else's information. So once you get into like layer 2 and like more complicated smart contract games, then it becomes more important to kind of wait for longer guarantees of finality.
So two things. One, so just to like recap, the transaction is generated, sent into a block. The block includes that transaction. Mm-hmm. That block then starts getting a bunch of attestations. That's like, you know, you're like 2 or 3 levels deep. And then now that block is a child of other blocks that have attestations. Now you're doing even better. And then that block gets included in a crosslink, which is kind of like the friendly finality gadget for shard blocks. Mm-hmm. And then that block gets, or that beacon block gets justified and then finalized. Okay, cool. And then, so for each one of these stages, I don't know, do you think that you could like assign a random heuristic-based monetary value that you would like to aim for? Just like in terms of like, oh, this amount of security. Is that possible even?
No, because like the security gradations do depend. Like the security gradations that come before finality do depend a lot on like network latency and honesty assumptions. And they depend on like what kind of counterparty you're dealing with. So like as in like the payment example versus like auctions.
Exactly.
Another thing I mentioned, by the way, is that you can do a trick where you can reduce the time to finality from 2 epochs to 1, or to 1. Basically, the trick is that you can have attestations in every shard simultaneously be messages pre-committing to only finalize specific things, right? And if you do that, then you can kind of get off-chain detectable de facto finality after like 1 epoch plus epsilon instead of 2.
And you don't halt because?
No, you don't halt basically because people would only do that if the chain actually is like at the top of the fork choice rule and it was justified and everything was okay, right? So this is a kind of category of optimizations that's worth looking into, right? That you can, like basically even though the main set of consensus messages on the main chain, you can do validators can sort of voluntarily constrain themselves inside of shards, and this could make finality happen faster. V, are you listening? This is fun stuff. Okay, cool. Yeah.
I guess one thing to mention is in the failure mode where finality takes a very long time, then these partial confirmations start to degrade. So, for example, the crosslinks, they don't have to be finalized necessarily. I mean, the main role of crosslinks, I guess, is to ensure availability, not necessarily finality. And so you can have the process of creating crosslinks continue even if finality doesn't happen, and so you have all these unconfirmed crosslinks, and some of them might not make it to finality.
What's the advantage of that?
The advantage of delaying finality.
So you have to delay finality in those cases where more than a third of, or more than like whatever. Well, you definitely have to. Sorry, I have to be pedantic because Vlad is here. You definitely have to delay finality if 1/2 or more of nodes are offline. And like you definitely have to delay the strongest possible degree of finality if any nodes are offline. And like between that there's a spectrum, and like it can be algorithm dependent. Okay, Vlad, give me a thumbs up, whatever. Yeah. Okay, back to 2/3 thresholds. Yeah. Okay. What's next?
I can throw in a question.
Okay.
So what's the full level of responsibilities of the beacon chain? Like all of it, what does it have to do?
Sure. I did make a list, I think. Number 1, maintain the random number generator. Number 2, maintain its own fork choice and maintain its own finality. Number 3, maintain the validator set and process validator incentives, process slashing, process validators coming in. So validators could like come in, deposit from either a shard or from the proof of work chain, and process withdrawals. Number 4 is to include crosslinks. That's basically it in terms of what the beacon chain does.
And every change to it requires a hard fork.
Yeah, I mean, like, there's probably some category of like weird changes that you can do with a soft fork or even a velvet fork. So like one example was, velvet fork is like a poorly defined term for anything softer than a soft fork. So like, one example is that we can change the beacon chain's fork choice rule from being like block counting to being ghost. Or potentially you could even have some clients run block counting and some clients run ghost, because if, unless you have like 50%, close to 50% malicious, they'll just always agree with each other.
In terms of what the shards do beyond like what a normal blockchain would do is pretty much just the attestations, which is kind of a new layer of, at least for phase 1, just the attestations.
We've kind of gone back and forth about this, because like delayed execution is, on the one hand, nice, but on the other hand, like I remember when especially when we talked about it in Taipei, people like there was a lot of kind of like negative feedback about it, basically because it's like it breaks the nice clean Ethereum model and it requires it basically doubles the complexity because you need separate fork choice rules and separate finality rules for figuring out where state got executed. So. Like, if we can figure out a reasonably simple model, sure, but I feel like the wind is currently leaning somewhat towards state roots just being integrated, but I don't know, maybe other people are thinking differently.
So does it have to be one or the other, delayed execution or stateless clients?
Yeah.
When it comes to calling the contract on another shard, does it have to wait till the end of this timeline?
Yes. Well, so A calling B, basically you do have to go through a crosslink to have an effect, unless you use one of these alternative execution contraptions, right?
Going through a crossing.
Yeah, no, so the idea is that if you're using one of these alternative execution contraptions, then you could potentially have instant cross-shard transfers where it's the the kind of finality of the ability to get everything you think you'll get because of the transfer is conditional on the cross-link and on the whole thing getting finalized. So it's but in an optimistic sense, the sort of mechanism could allow you to move money around or do whatever you want in a few seconds.
How will people be splitted in the shard chain? Like, will it be geographically, latency based, or equal number of people on all shards?
So at the system layer, in terms of proposers and attesters and maybe executors might be a new class or a new role for the execution. That's kind of randomized on a shuffled on a randomized basis. As for the users and at that layer, I guess it would be in terms of applications that get built on specific shards. So initially, at least for the foreseeable future, there won't be much shuffling, or there'll be no moving around contracts across shards. But things like load balancing might be something we want to do in the future. So on that point, I have asynchronous calls here. That's asynchronous calls between contracts. And if we do go that way, that would make it easier to do load balancing, whereby if you have a shard that becomes too big, then you can start splitting it into two separate shards. And from the developer's perspective, making a call to a contract in the same shard is the same thing as potentially making a crawl across these shards.
Maybe I'll suggest a topic change to cryptography.
Okay, yeah. So I guess from a cryptographic standpoint, we want to make use of lots of recent or very cool and powerful gadgets, some of which are non-quantum secure, but at the same time we want to reconcile with being very conservative and having the end game use only quantum secure crypto. And so, as I was mentioning yesterday, there's two places where we potentially will use non-quantum secure crypto. That's in the random beacon, number one, and number two in the aggregation. And one of the main ways we're looking forward in terms of being quantum secure is with stocks. Stocks are particularly nice because they provide a generic solution, so you have them once and they can solve all your problems. There will be a discussion about stocks tomorrow. But I guess one of the challenges with stocks is around performance, like the size of the proofs and also the prover time. And one of the things where we can have a significant contribution at the protocol layer is by using primitives which are friendly to stocks. And one of these is the stock-friendly hash. So one of the things we're considering doing is basically deprecating SHA-3 in favor of something more stock-friendly. The technicality here is that I think when you look at the hash function, you want to look at the multiplicative complexity of the circuit once you kind of lay it out. And by that I mean like the number of multiplication gates you need to implement it. And it turns out that SHA-3 and most of the hash functions out there are not super friendly. But one candidate we're looking at is called MIMC, and it's very friendly.
Here, I'll just like draw it out quickly.
It's called MIMC, M-I-M-C, and basically what you do at every round is you raise to the third power, and it turns out that creates a permutation in some setup, and then you XOR with some key, and that's pretty much it. And then you just repeat, between 100 and 1,000 times.
I don't know the exact concept, that's just like what it seems to be.
Yeah, around, yeah.
What is the key?
The round keys are basically just like numbers we agree on. So they're like magic numbers, and like realistically you want them to be like arbitrary and should be chosen by the NSA. No, just like digits and pi.
Okay. And you just decide that one time, and now everyone uses that forever.
Are some numbers better than ours in that respect?
So I think what you want is like you basically want to have sure. So you want to have numbers that have the smallest risk of having mathematical structure that can be exploited to kind of simplify this expression, right? So like one one obvious example of a bad candidate is just choosing 0. Another example of because if you just choose zeros, then this just becomes like x to the 3 to the k, and that's like trivial to simplify. Another is that if you use even just like a single constant, or possibly if you even use like successive powers, I think like there's a risk that you could do kind of mathematical simplifications. Like basically, like one thing you could consider doing, right, is you could consider having the k's be some kind of like successive powers of a number in some totally different mathematical structure. Like the goal is to like you want them to look to be as close to random as possible. So the scheme is probably the most secure if they literally are the output of something random. And if it's not random, as long as its kind of mathematical structure doesn't align with the mathematical structure of the finite field you're working with, then like that's safer. Yeah. MIMC is interesting because it can actually be used to solve both of our problems. So first, like one of our problems is that we need a Stark-friendly hash function, and we need a Stark-friendly hash function both because we want to do Starks over basically to prove claims about the Ethereum blockchain, but also because if you want to have a Stark-based aggregate signature, then it turns out one of the cheapest ways of doing it is that if you use a Lamport signature, which is basically just a bunch of hashes, then you can do a Stark that proves a whole bunch of Lamport signatures on the same piece of data, and that requires a huge pile of hashes. And so if each individual hash is very Stark friendly, then it becomes quite fast to run through the whole thing. Another thing, the other problem that it solves for us is the VDF, right? So there's one really nice construction that you can use to make a VDF, and like based on the same permutation. And what you do is you basically run it in, hold on. Right, so basically imagine you do the permutation, first of all, in a somewhat different direction, where you say XOR, KN, then over here, X to the, I think it's P plus 2 over 3, or something like that. Something like that, yeah, and then possibly, yeah. Hold on, actually, no, P plus 1 over 6, that's what you need. Because like X to the P plus 1 is X to the 2, because like from Maslow's theorem, like rolls over P minus 1, and then the 2 over 6 gives you that, yeah. Then you have another XOR gadget, then you have that. And then eventually hits the end. So the idea is, right, that like this permutation is the inverse of MC, right? So because this is a permutation, then every single piece of this can be inverted, and you invert it basically just like running through it backwards. Now XOR is obviously the inverse of XOR, and the inverse of X cubed is this funny expression, and this is just like a much larger exponent. And so running the permutation in reverse costs about like maybe 200 times more than running it in the forward direction. And this is nice because, first of all, that gives you a kind of weak proto-VDF already, because if you have a computation where it takes, say, 5 seconds to run in the forward direction, but then like 25 milliseconds to run in the reverse direction, like that's almost good enough to be a VDF all by itself, though not quite. Like basically the reason why not quite is because we want to have large safety margins in case someone has ASICs. We want to make verification be friendly to like light clients and all those other things. But here's what you do, right? So first of all, in order to run the VDF, you would basically, well, the way it could work is you would run the permutation in the hard direction. Then when you're done running it in the hard direction, or ideally somehow you start even before, you run it in the easy direction, and when you run it in the easy direction, you do a Stark of the easy direction. And then the Stark of the easy, basically the idea is that if you can get the overhead of running a Stark in the easy direction, if you get the overhead of a Stark to be less than the overhead of running the function in the hard direction versus the easy direction, then imagine the hard direction takes like 10 seconds to run, then the easy direction by itself might take 0.05 seconds. But then if the overhead of a Stark is, say, only 100, then this goes up to 5 seconds, and so it doesn't actually affect the runtime of the VDF that much. So one piece of good news is that I spent the last couple of days trying to implement Starks from what I know of the protocol, and like I used this as an example, and it's obviously kind of very heuristic, but we have the numbers I have is basically that the Stark overhead can be brought down to about a factor of 600. And the reason, now if you read the literature, you'll hear about overheads of like 50,000, but the reason why that's the case is because like you get numbers like 50,000 because you're doing Starks over general purpose computation. And when you're doing them over general purpose computation, every single bit operation, every logic gate turns into a finite field operation. But here we're doing a circuit that's like naturally very arithmetization friendly, and it's already over finite field operations. So you just have a smaller amount of Stark overhead, and then maybe a fact, like 600 is very preliminary. Like you can obviously optimize both the MIMC itself and the Stark more. But then if you want to go below 100, basically what you do is you just like parallelize the thing and run it on an 8-core CPU, and then 600 over 8 is? Yeah, 75, yes. And 75 is like lower than this. So like basically there is hope, right? And even if there isn't hope, then you could potentially just like restrict. GPUs can get way more parallelizability than a factor of 8. So like it should be fine. So I believe that So this is the sort of thing that needs more kind of like collaboration with academics, and fortunately, we just gave a pile of money to the Stanford Blockchain Research Institute and so forth, so people are happy to help. And not just them. Like I've had some chats with like the Zcash team. We've had chats with other teams. So there's plenty of academics that are like actively working on this. Heuristically speaking, I will say that I don't. So first of all, like this kind of construction was conceived in. Like this is inside of a finite field where the finite field itself is small enough that the discrete log problem over the finite field is definitely solvable, right? And in fact, the constructions they advocate are not even over, they often don't even talk about constructions over prime fields, they talk about binary extension fields. And over binary extension fields, the discrete log problem is even more solvable. So, like basically, it seems to me that the discrete logs being trivial, even that by itself basically doesn't really help you like do anything funny to MIMC. And the intuition is basically that like MIMC does not using the polynomials as any kind of trapdoor. MIMC is basically just using polynomials as a way to kind of shuffle bits around and create mathematically complex relationships between bits. Now, this is, as I've said, this is very heuristic, and this is as a hash function, right? Like generally, you want your hash functions to be kind of jumbled up and confusing, so they're resistant to analysis. But like here, well, okay, so like this is like one of the mathematically cleanest things that's ever been proposed as a hash function. So that by itself kind of makes it scary. The reason why it's not super scary is because like this relationship expressed as a polynomial still has a very complex expression and a degree of like 300 to 3000. So it's like you can't use for example, the degree isn't 300 to 3000. The degree is 3 to the power of 100 to 1000. So you can't do things like Lagrange interpolation and the standard stuff that you can use to break things that are close to being linear. But like this is worth more analysis, and like maybe mathematicians have more insights. And so in all of the various kind of academics that we're talking to can definitely they've been working on they're interested in working on these problems because like a lot of people in the blockchain space are very interested in them.
Just backing off a little bit, this MIMC-based start, is this for the verifiable deterministic function?
Yes. So MIMC is a kind of core primitive, and it can be used as a building block for a hash function. So there's a kind of fairly standard way, like the sponge construction, where you can take any kind of like reasonably random looking permutation, put it into the construction, it turns into a hash function, or you can just use the thing as is as a PDF.
So it's not an alternative to BLS?
Oh no, so the alternative to BLS signatures is basically an aggregated Lamport signatures, right? So like a Lamport signature is basically just like a pile of hashes where you reveal a subset of hashes based on what the value is. Each Lamport signature, verifying each Lamport signature is on average like the 128 hash calculations. And so if you're going to aggregate together like 1,000 Lamport signatures, then that's basically you're doing a Stark over 128,000 hash calculations, and which is potentially totally within the realm of possibility for a GPU. But,
So this roadmap is using a Stark for the PDF, but not a Stark for...
Oh no, so the roadmap is in the short term using BLS aggregation for aggregate signatures, and for the verifiable delay function, it could be a Stark or it could be one of the other constructions that came out of like Stanford academic land recently, which basically is kind of like a fancy probabilistically checkable proof for x to the power of 2 to the power of n for very large n. So there are other constructions that are coming out, but like they're not quantum secure. They rely on factoring hardness, and they rely on like other kinds of mathematical structure. But like in the future, like basically there are purely hash-based solutions for kind of every cryptographic ingredient that we've talked about so far.
Okay, so let me begin with that. I'm happy if I understand like 1% of that. Probably not. So my question, as usually, may be totally off, but can you highlight the part that makes that actually like quantum resistant? Because my understanding about that is that in the future, quantum computers may just be efficient enough to brute force
so
these
the thing
things?
to keep in mind is that quantum computers can solve very specific problems. They can solve order finding, which makes them means they can do factoring very easily, and they can solve the discrete log problem. Right, so, and that basically means that they can break anything that's like elliptic curve based or based on any other kind of finite cyclic groups. So, the quantum computers cannot break hash functions. Now, they are somewhat better at breaking hash functions, which means that we have to, use the full 256 bits of every hash, and we can't go down to 128 bits or whatever. But within that context, right, like basically, like quantum computers cannot break hashes, and Starks rely purely on hashes and information theory for their cryptographic assumptions, right? So, an information theory basically just means math, like it's mathematically, impossible. And now, technically, like blah 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 Fiat-Shamir involves properties of hash functions, but like as long as hash functions are continue being secure, you're fine. So, the idea here is that the Ethereum blockchain is going to be dependent on hash functions no matter what we do, because we need them for Merkle trees, we need them for stateless clients, like scalability, we need them for so many things anyway. It's like hard to imagine a hashless blockchain. And so if we're gonna be rest on one ingredient, then we can achieve kind of minimal assumptions, but just if we need to, by kind of shoving everything onto solutions that just piggyback off of that one ingredient's properties.
Thank you.
One cool thing of using MIMC for the sparse Merkle tree, which we might talk about later, is that we can have an optimization on the stateless clients. So normally with stateless clients, you come in with your data along with a bunch of very large witnesses proving that the data matches the state. And with Starks, potentially, we can take all these witnesses and compress them, making stateless clients more viable as a strategy. But to answer is MIMC quantum secure? I guess right now we don't even know if it's collision resistant. We don't even know if it's secure against normal computers.
There are heuristic arguments in the paper that say that it's very good against kind of traditional forms of cryptanalysis. Basically the idea is that x to x cubed is as perfect as possible in terms of being nonlinear in a specific way, but there is basically because it's a relatively simple arithmetic representation, that itself could lead to other kinds of mathematical attacks, and we totally need a good period of time to get the thing cryptanalyzed. A couple years ago. Yeah.
I think it came out more than a decade ago, so quite a long time ago, but it was actually broken, I think.
No, I think what happened is that there was an earlier kind of crappier version that was broken, and I forget for what reason, but I think it's because they either they don't have round keys, or they use the construction in such a way as to make it no, I think what happened is that they used the construction in a different way. Basically, they might have done the cubings in parallel instead of in series, and that made the arithmetic representation of the entire thing have a low degree. So and when you have a very low multiplicative degree, then let's say, for example, if the multiplicative degree is say only 100, then as soon as you get 101 hashes, you can basically use Lagrange interpolation and figure out what the degree 100 polynomial is. And once you have that, you can figure out everything else you want about you can kind of fully analyze and break the function.
So you want your degree to be so insanely high.
Yes, and in this case, the degree is 3 to the power of 100.
Right. I think they were using 10 before, which made it liable to this attack.
Right.
There's 5 minutes.
5 minutes left. Sparse Merkle trees?
Oh yeah, sparse Merkle trees are awesome. Okay, so basically here, and I think Alexei talked about this a little before, but the basic construction is fairly simple, right? You have a root, and then that root by itself has 2 subnodes, and then those subnodes themselves have more subnodes. Now, unlike other kinds of trees, the idea is that here at the bottom level we actually have 2 to the 160 nodes representing the entire set of 2 to the 160 accounts, right? So it's like a tree that has 2 to the 160 nodes at the bottom, then over here you have 160 levels. Now, this basically, it's like an ideal binary tree, which means that, you know, if it's very simple to figure out how to insert, how to look up, and how to do everything. There's a few questions here, right? So one is, this thing has 2 to the 160 size, how the hell can you even construct it in less time than it takes to find a hash collision? And the answer is that, well, in an empty tree, these nodes are all zeros. And so the level 1 nodes are just all going to be hashes 0 and 0. So the level 1 nodes are going to be the same. And the level 1 nodes are the same, so the level 2 nodes are going to be the same. And then the level 3 nodes are going to be the same, and so on and so forth. So it only takes 160 hashes to construct a full empty tree. Then from there, basically, every individual update can be done in kind of log n time, and you're never kind of, like basically in all of those cases where, in all of the cases where you have like identical kind of like empty subtrees, you only actually need to store it once. You don't actually need to you know, store every single kind of copy of the node of the tree that's empty. And so like basically you just start off with a database that contains these values, and then you just like run the insert for whatever you need to, and then you can run a lookup for whatever you need to, and that's enough. So that's the answer to why they can work at all. Now, there are 2 inefficiencies that led me to kind of not take this seriously earlier, but it turns out that these inefficiencies both have solutions. So the first inefficiency basically is that for a Merkle proof of an account, normally, let's say this tree has like 2 to the 32 real accounts, right? Then the Merkle tree, instead of the Merkle tree being basically 32 bytes times 32 long, the Merkle tree becomes 32 times 160 long, and so the Merkle proofs are 5 times longer. But there is a solution. So here's the solution, right? So let's say, for example, we have a situation where we have this tree that has 8 nodes, and let's say only 2 of the nodes are non-zero, right? And let's say these nodes. Then the only, like basically, we can look at these, I'll highlight these nodes, right? But let's say you actually are looking for, you know, like some node in the middle, right? So one thing that you might, so let's say, for example, that you want a full proof of this, right? So here's one thing that you can figure out. So first of all, you clearly have this node, so you need this node. But then, in order to calculate this node, you need this node. But guess what? This node actually is a level 0 empty subtree. And we already know what a level 0 empty subtree is. And so we can use 1 bit to represent the fact that there's an empty subtree. And then the recipient knows what the hash of an empty subtree also is, and so a level 0 empty subtree also is, and so the recipient can extend the 1 bit back into being a hash. Then we go up to over here. Well, over here in a standard Merkle tree, you need this value. Well, this value is the root of a level 1 empty subtree. And so that's also something that we know. Then finally over here, you need this value, and this value is non-empty, and so this value actually provide a hash. So altogether, you can create a very simple representation that basically says, like, here's a bit field that says, like, which of the, at what heights do I have empty hashes? And then here are my actual hashes. And so you basically get, like, very close to the 32 times log n optimum. So that's, and I actually did, and I implemented this, and it turns out that the overhead on even the simple construction, where you have a 32-byte bit field, is smaller than the overhead on like pretty much every tree that we've had so far. Like it's a maybe 20% size improvements on Merkle proofs. The second thing, now the second challenge is, well, if you're going to actually poke through the tree, then possibly you're going to need, if you do it naively, right, if you just like store the tree as a level DB hash map, then you're going to need like 160 lookups through the level DB hash map instead of the current value, which is like basic, well, it's not even 32, it's going to be 8, because it's 32 divided by log of 16, right? Because the tree is hexary. So, like, that might now, that has a solution as well. And the solution basically is that instead of storing the tree naively, basically client side, any client can use whatever tree they want, right? So client side, a node can choose to basically represent like this entire branch as a single object. Client side, the clients can choose to represent all of this in some kind of red and black tree. Client side, a client can choose to represent this in like some kind of Patricia tree that has some particular structure. And if it's a client side, the client could choose to represent this in a just like regular binary tree and then use a private seed to kind of prevent the to randomize the tree to prevent the attacker from getting from creating a worst case situation. So, like basically, you can design the database logic so that you can actually design the client-side database logic to be like pretty much optimal in whatever way you want, and the kind of like the in-database structure of pointers does not have to directly correspond to the structure of hash pointers. So you can potentially get even better results. So like, and I'm not the expert, but like one very simple optimization, right, is that a database read basically takes the same amount of effort if it goes anywhere up to 4,096 bytes. And so instead of having a tree where it's where it has 16 elements on every side, so you have like 16 times 32, you could have a tree that has 120, where every single hop down the tree takes you 7 bits, so it's 128, and then 128 times 32 gets you to 4,096 bytes, and that would basically mean that instead of doing like 7 hops, you'd be able, or like 8 hops, you'd be able to go down to something like 5 hops. So like there's basically like once you stop assuming that the database the database level pointer structure has to follow the hash level pointer structure instead of like being a subgraph, then all of these optimization opportunities become available, and like you can basically get whatever you want that's close to optimal. Yeah. Yes. The other really nice thing about this, by the way, is yes, it does. And the other nice thing about this, by the way, is that because the function for verifying Merkle branches is like absurdly simple. Number one, this becomes way more Stark friendly because you don't have to do like RLP decoding inside of Starks. Number two, it becomes way more Ethereum contract friendly. It just becomes easier for pretty much anyone to implement. Number three, it becomes possible to do constructions like proof of custody or like erasure-coded data availability proofs over the state tree, which you can't do now because the state tree is way too unstructured. So, basically the kind of like the much greater level of structure in this particular in this kind of tree makes it like opens up a lot of these possibilities.
So the size of the proof over the network, let's say when you're communicating with a smart contract, will still depend on this abstract structure?
So the size of a proof when you communicate over the network will depend on this compression algorithm, and it'll be 32 log n. Even adversarially, yes. So like basically the idea is, right, that like the Merkle branches are, okay, so first of all, like the worst thing that an adversary can do is that an adversary, if you have a node over here, an adversary can kind of like send one way to accounts beside it in order to kind of like fill it up, right? But that's something that you can do with a Patricia tree today.
Yeah, I'm not saying it's any worse.
Yeah, exactly, yes. The worst case is definitely like basically equivalence to the worst case with a Patricia tree.
Okay.
Yeah. Actually, I think in terms of proof size, it's slightly better because the worst case with the Patricia tree is that the length is like 512 bytes multiplied by 64, whereas here it's 32 bytes multiplied by 256, which is 4 times less.
It also seems like you could probably do some funky RLP.
Yeah, well, RLP tends to, like, I don't think there's any like serious issues, but it does introduce like 2 or 3 bytes of overhead pretty much always.
So the agenda for the session did say it's about phase 2, and yesterday's was about phase 1. Is there any decisions at the phase 1 that impact or constrain what you can do in phase 2? Because I know with phase 2, at phase 1 it's only dealing with data blobs, so shard blocks are only ordering these data blobs. Are they completely orthogonal and independent, or are there things that, if it's chosen at phase 1, you have to, and you want to do something at phase 2, you have to go back and change phase 1?
I'd say they're very decoupled. One place where they do meet is on the execution games. We haven't really totally figured out which strategy we want for the execution games, and so I'm slightly uncomfortable there, but just the general heuristic is, for me, is that the execution games are much simpler than the consensus games, because the consensus games are about determining what data goes into the shards, and once you have that, and you feed it as input to the EVM, which is kind of assumed, then computing the output is just a deterministic execution game, and it's much simpler than consensus. But because we're taking this kind of unorthodox approach in the blockchain space to decouple data from state, there are some risks. And in terms of trade-offs, we could have delayed execution, we could have stateless clients. It could be more overhead, slightly less security, or more latency. I think there will be a trade-off somewhere, but I'm hopeful that it will be quite small.
Regarding overtime now. Oh, okay. Overtime. So I don't understand how you decouple the data from the state, or did I miss something?
So there is stuff that that's kind of background that people from a Type A event might know that's that we didn't state, which is that basically the idea is what happens if we want to have the possibility of cross-shard communication that happens faster than crosslinks, right? And the problem there is that basically you have these two shard chains that are decoupled, at least temporarily decoupled at the data layer. And so imagine if you have one operation here, and then a contract calls some other contract, and then over here it does something, right? The problem is basically because there is no shard layer dependency, what happens if suddenly this gets this fork reorgs? And this does not reorg. So then the effect happened, but the cause did not happen, right? So in order for this to kind of not be an issue, you basically have to allow for the possibility for state roots inside of here to recalculate without the data roots also recalculating. And the way you do that is you have this kind of somewhat decoupled state execution game where the blocks aren't kind of tightly coupled with state roots, but instead you basically have some separate state root providing game, and over here the state root providing game would just say, oops, here's a new state root.